So, as we said, water is an amphoteric substance, which means it can act as both an acid and a base. And so you can then make two water molecules react together in an acid-base reaction. And so this is showing in this reaction. On the left side, you have one molecule of water. That first molecule will be the one that will act as an acid. And then a second molecule of water, and this one will act as a base. When the molecule of water acts as an acid, it's donating an H+, and so H2O, when it donates an H+, it becomes OH-, right? Because the one of the bond becomes a lone pair, and that makes it a negative charge on the OH-. And so OH-, to the right of the arrows, here is the conjugate base of water as an acid. The other molecule of water acting as a base will accept the proton. And so one of the lone pair will become a bond with another hydrogen. And that's going to be the H3O plus to the right. The proton comes with a positive charge, so that's why it's positively charged. And this H3O plus is the hydronium ion, and that's the conjugate acid to the base, to water as a base. So if we write the equilibrium constant for this equation, again, it's the concentration of the reactant over the concentration of the product. And so here, let's call it Kw. Kw is concentration of product, which means H3O plus times OH-. They have no exponent because their coefficients are 1. Over the concentration of reactant, but here you can see that on the reactant side we only have 2 molecules of water, which is our solvent here, or liquid. So as a liquid, it's not included in the K value. So then the Kw will stay as concentration of the hydronium ion times concentration of the hydroxide ion. This Kw can be calculated and has been calculated at room temperature. It has been found that the concentration of H3O plus equals the concentration of OH minus equals 1.010 to the negative 7 molar. The reason why these two concentrations are equal, it's because you can see that when water dissociates, you make both ions at the same time. You cannot make one without making the other. So that's why those concentrations have been found equal in pure water, and they have been found to be equal to 1.07 10 to the negative 7. 1.01 10 to the negative 7 molar. So if we plug in the value into the Kw expression, it will become Kw equals 1 10 to the negative 7 times 1 10 to the negative 7, which is equal to 1.0 times 10 to the negative 14. When you multiply two numbers with the numbers of the same kind with exponent, the exponent are added. So 7 plus 7 or minus 7 plus minus 7 equals minus 14. Remember how the equilibrium constants have no unit. So this is staying as is. And so Kw is a constant. It's always equal to 1 10 to the negative 14 for all aqueous solutions at 25 degrees, not just pure water. It happens that all aqueous solutions have this value staying true. And so it's only in water that, pure water, that the hydronium ion concentration equals the OH minus concentration. But in most solutions, they are not equal, but their product the product of their concentration stays equal to 1.0 10 to the negative 14. This Kw is called the ion product constant for water. And it's found in your yellow packet. If you go back to page 5, the ion product constant of water, you can find it in the middle right. It's given to you because it's used to do some calculations of concentration. So, as I said, all aqueous solutions contain those ions, the hydronium ion and the hydroxide ion. And so, depending on which one exceeds in number or the other, you will classify the solutions as acidic, neutral, or basic. Let's start with when the concentrations are equal, when the hydronium ion concentration is equal to the hydroxide ion concentration. When they are equal, they are necessarily equal to 1 10 to the negative 7 molar. The one here is implied. It's 10 to the negative 7, but it's 1 times 10 to the negative 7 molar. When you are in this case, when you have reached these conditions, then it's a neutral solution. It has to be exactly equal. Whenever you deviate from those concentrations being equal, you will get either an acidic solution or a basic solution. Let's look first to the left. If the hydronium ion concentration is larger, which means greater than 10 to the negative 7, so hydronium ion concentration greater than 1 10 to the negative 7 molar, then the hydroxide ion concentration will necessarily be lower, smaller, so that their product is still equal to the Kw. And so when one increases, the other has to decrease. And when it's the hydronium ion concentration that is larger in value, then we call that an acidic solution. So on the left, you have an illustration of what is an acidic solution. Now, if on the contrary, you have the hydroxide ion concentration being larger than the hydronium ion concentration, which means the hydronium ion concentration is less than 1 10 to the negative 7 molar. Whenever it's under that value, you have a basic solution. And again, if the hydronium ion concentration is small, then the hydroxide ion concentration will be large to compensate, so that their product, when you multiply those two concentrations together, you still get the Kw value. So you need to remember these classifications of the solutions, that whenever the hydronium ion concentration is larger than 1 10 to the negative 7 molar, it's an acidic solution. When the hydronium and hydroxide ion concentrations are both equal to 1 10 to the negative 7 molar, it's a neutral solution. And when the hydronium ion concentration is less than 1 10 to the negative 7 molar, it's a basic solution. This you have to remember, it's not in your yellow packet. So remember that. So this Kw expression is often used to calculate concentration of either the hydronium ion concentration or the hydroxide ion concentration. So let's look at, for example, if you know the hydronium ion concentration and you want to calculate the hydroxide ion concentration. So you will use this Kw formula. And because we know Kw, it's always that 1 10 to the negative 14 value. We know H3O plus in this case, and we want to find OH minus. So we need to solve for OH minus. To isolate OH minus, you need to divide both sides of the equal sign by H3O plus. And so you can see that on the right side of this equal sign, if you divide by H3O plus, both H3O plus cancel, and you're left with just OH minus, and that will be equal to Kw over H3O plus. Kw has a known value of 1.0 times 10 to the negative 14. And so when you want to calculate your hydroxide ion concentration, you plug in your hydronium ion concentration in the denominator, and that will give you your hydroxide ion concentration. If now, on the contrary, you know the hydroxide ion concentration and you want to calculate the hydronium ion concentration, again, you start from the Kw formula. This time we know Kw and OH minus. We want to get rid of H3O plus on the right side of the equal sign. So for this, no, sorry, we want to get rid of the OH minus, excuse me. We want to get rid of the OH minus because we want to calculate H3O plus. So we will divide both sides by OH minus. If you divide both sides by OH minus, you can see that OH minus cancels on the right side, and you're left with H3O plus equals, and then the other side will have Kw over OH minus. Knowing the value of Kw is 1 10 to the negative 14, that's the formula you would use. And so you can see they are very similar. So if you are not so sure about how to get back to these formulas, what you need to remember is that the Kw will always be in the numerator, and then if one concentration is on one side, then the other will be on the other side in the denominator. It's always in that configuration. So let's check your learning by doing practice problem number 7 and 8. So practice problem 7 and 8. So you can pause now before getting to the answer of practice problem 7. That problem is asking for the hydroxide ion concentration if the concentration of H3O plus in a cup of coffee is 1.0 times 10 to the negative 5 molar. And after that, after you've calculated that value, decide if your coffee is acidic or basic. So we have seen that to get the concentration of the hydroxide ion, we need to use the Kw expression, divide both sides by H3O plus, and then we have OH minus by itself on the left side of the equal sign, equals Kw over H3O plus. Kw is 1.010 to the negative 14. You plug in the value for the hydronium ion, and that's 1.010 to the negative 5. Do that in your calculator, and if you use the EE key, as I taught you, you should not make any mistake and get 1 times 10 to the negative 9. The way to verify that, if you're at ease with numbers raised to an exponent, here it's 10 to the negative 14 over 10 to the negative 5. If you move 10 to the negative 5 to the numerator, it changes its exponent to positive 5. So it's 10 to the negative 14 times 10 to the negative 5. When you multiply numbers that have exponent like that, same numbers that have an exponent, you add the exponent. So negative 14 plus 5 makes negative 9. So you could verify that value mentally also. if you're at ease with this kind of calculation. So here, even though Kw is unitless, the concentrations do have units. And when you are asked to calculate the concentration, you need to add capital M for molarity, right? The hydroxide ion concentration is 1.010 to the negative 9 molar. And we keep 2 sig figs because we had 2 sig figs in both values. Now, is this acidic or basic? If you look at the concentration of OH minus, it's 110 to the negative 9, and the H3O plus, it's 110 to the negative minus 5. 110 to the negative 5 is a larger value than 110 to the negative 9, because 110 to the negative 9 means you divide 9 times by 10. 110 to the negative 5 means you divide 1 5 times by 10. So that's a smaller, that's a larger value than 110 to the negative 9. So the concentration of H3O plus is larger than the concentration of OH minus. Even though both values are very small, the H3O plus is still much larger than the OH minus. If we have more H3O plus, you can associate H3O plus with acids, and that tells you it's an acidic solution. So yes, coffee is acidic overall. Practice problem 8, which is a continuation of practice problem 6. It gives you the concentrations of HCN, CN minus, and then the hydronium ion. And you have the equation. There is extra information in this problem, right? When you are asked to calculate the concentration of the hydroxide ion, OH minus, you don't need all of this. You only need H3O plus, right? So the way to solve this is to, again, take the Kw formula, because when you have questions asking for a hydroxide ion concentration and you're given the hydronium ion concentration, you want to use the Kw formula. Here, it will be OH minus that you want to isolate. Divide both sides of this equation by H3O plus, and you get OH minus by itself, and it's equal to Kw over H3O plus. Next, you plug in the values, and Kw is 1.0 times 10 to the negative 14 over the concentration of H3O plus. Plug in the value of H3O plus, and it's 4.9 times 10 to the negative 5. So do that in your calculator. And again, if you use the EE key, the calculator will know that the times 10 to the negative 5 belongs to the 4.9. If you don't use the EE key and do times 10 power, your calculator might move the times 10 to the negative 5 to the numerator, and that will give you, so let me calculate that. That would, well, that would be giving you, yeah, hold on. So if you are not using the EE key, and that your calculator moves the 10 to the negative 5 to the numerator, because, for example, you haven't used the parentheses, the calculator answer will be 2.0408 times 10 to the negative 20. If you get that, you know that you need to use the EE key so that your calculator knows to keep the coefficient with the power of 10. So the calculator answer is 2.0408 times 10 to the negative 10. We have 2 sig figs on the numerator, 2 sig figs in the in the denominator, so we keep two sig figs. And so we run to 2.0 times 10 to the negative 10. And don't forget to add the unit of capital M for molarity. So we need to decide if it's acidic or basic formula. And again, you look at the hydroxide ion concentration. It's 2.0 times 10 to the negative 10, which is a very small value. But the hydronium ion concentration is 4.9 10 to the negative 5. 10 to the negative 5 is a larger value than 10 to the negative 10. So again, we have more H3O plus ions than OH minus ions. And so because of that, it's going to be acidic, right? When your hydronium ion concentration is larger than your hydroxide ion concentration, it's an acidic solution.